Thank you. Good afternoon, everyone. This is the first time I'm at the beautiful city of Medicine Hat. And even though I just live 6 hours away from here, and the past summer, I tried to come for a visit. So I thought I was smart enough, no GPS, no map. And 6 hours later, I end up at a city. It's a different city. And I went back, I talked to one of my colleagues, and he asked me, where was the city you were at? I told him, Lethbridge. And his facial expression said it all. And I didn't tell him that wasn't the first time it happened. And it wasn't the worst experience I ever had. Actually, Lethbridge and Medicine Hat is not that far away, so I have a worse direction-wise trips experience I can talk about. But anyways, and this conference is all about getting smarter. So I have a high hope for this conference. I hope after this conference I can find my way easily back home. And this conference actually is talking about farming smarter. And let me talk about something related to farming. And I'm developing a technology that uses Nano-Biosensors for sclerotinia, stem rot, disease forecasting. Sclerotinia stem rot is one of the most devastating diseases in canola farming. Scientists have worked very hard to try to find a way to forecast it. Now we have checklists. A checklist is a set of questions you have to answer before you can make spray or non-spray decisions. And questions such as, did you grow the same crop the previous year or years? Did you find sclerotinia stem rot in the same field the previous year or years? How wet is your field this year? So on and so forth. So Saskatchewan gave you 6 questions. In Manitoba, you have the following conditions to evaluate. So ground is damp to white. Canopy is moderately closed to closed. Canopy is still damp to white when walking through the field at 10 a.m. I'm always amazed by how accurate things can get. So if you go to Manitoba, you land up at a farm field, you see all the farmers land up before their field at 10 a.m. and ready to walk through their field. And the field is at 20 to 50% flowering. If you meet all these conditions and you have a Epichycia in your field, you need to spray. Alberta scientists are the hardest working scientists of them all, so we gave you 15 questions. So after answering all these questions, you thought, oh good, I don't need to spray. So wait a second. This is like you read a flyer. You want to buy a pair of shoes. There is a flyer in front of you. It says 50% off. But don't run to the store just yet. You have more to read. So in the little fine print, it says if you have to buy the first pair at regular price. So if you don't need 2 pairs of shoes, don't rush to the store. It's not worth it. And they usually make it in very fine print, so they try hard to trick you. If you don't want to be tricked, you have to read hard, especially for the people who need reading glasses. So after finishing the questions, AKA the checklist, and you thought you didn't need to spray, so read this. This checklist is not always reliable because sudden weather changes can cause infestations to occur unexpectedly. For example, if you have lots of rains and the spore blooming happens, So you know now you may need to spray or may not, depends on how many spores are there. So can you count them? If you know how, please tell me. I don't know how. So you need to decide if you need to spray or not. And the other statement says, scouting for epithecia can be time-consuming, but finding them is an excellent indicator of sclerotinia risk. But not finding them either means there is a low risk of sclerotinia or the scouting was ineffective. That means you didn't find epithecia. It doesn't mean they're not there. It's just you didn't find them. So spray or not. If you were to ask me, my suggestion to you would have been to flip a coin. You have a 50-50 chance anyways. And we also know we need to improve the forecasting technology. The problem we have right now is it's hard to find the epithecia. Therefore, it's hard to find if spores present or not, and how many spores are there. Are they reached the level that can trigger a disease outbreak, and when? So we can't send the farmer camp in the field 24/7 for about 6 weeks to find this out. So we have to find a solution. My solution is an in-field biosensor for real-time sclerotinia spore detection with specificity and accuracy. If I had told you this 10 years ago, you would have said to me, you're still young. Why? Because you still have dreams. But there has been lots of new technology development. Trying new technologies to old problems, you may find a pleasant surprise. And we usually say hit a jackpot. But don't get overexcited. There is no money in the jackpot, only hard work. So we think this biosensor technology may help us find a way to solve the problem. What is a biosensor? A biosensor is an extremely small device capable of detecting and responding to physical stimuli with dimensions on the order of 1 billionth of a meter. It is being developed right now for the use in medicine. So they are used for detecting DNA's proteins for disease diagnosis. For example, they can detect the glucose levels for diabetes. We think we may be able to use this biosensor for spore detection. So the idea is, in a canola field, it may or may not have sclerotinia stem rot, but we're going to put a spore collector anyways, and we send the samples collected, the spores, periodically to the biosensor detector. You can set it up based on needs, like 2 hours, 4 hours. You can send your sample to the biosensor, and the sensor will detect the spores. If the number of spores reach the level that you need to spray, it will convert the biosignal to electronic signal and send it to your cell phone. So you don't need to go to the field. By using this device, you just stay at your comfort home, then you find out if you need to spray or not. So this idea is not from the sky. It's based on lots of available technologies. There are billions of spores or other things in the air. How can you detect sclerotinia spores only? There is something called an antibody. A person gets immunized by influenza virus A, he will produce antibody against virus A. If a virus A attacks him, the antibody in his body he produced will recognize the antibody and tell the body to kill it. But if a virus B attacks him, he's out of luck. He still gets flu. That's how specific an antibody is. And the antibody only bind and catch and recognize the molecule that produced them, nothing else. And we need accuracy and acceptable level of detection. So use this sensor, we should be able to detect spore numbers at the level that will trigger the disease or lower. Anything higher than that is useless. How could we achieve that? We have nanotechnologies. After that, we need to convert the biosignal, the spore number, to an electronic signal so that we can transmit the information from the sensor to your cell phone. How could we achieve that? We have sensing technology and Bluetooth technology. So now let's get our hands right. Producing antibodies. Because this antibody is not commercially available, so we have to produce them. We vaccinated a rabbit, and we took samples before and after vaccination. We use ELISA to check the specificity of the antibody. So the blue line shows the sample taken before vaccination, and the right line shows the sample taken after immunization or vaccination. So we have high specificity antibody produced for our purpose. And how does a biosensor work? So in a biosensor, there is gold electrodes, and gold electrodes will form an electric field in the sensor. And we bind antibody to the electrode. The antibody serves like a police check stop for the drunk drivers. If you were a drunk driver, you were caught. If you had other hidden agenda, it's your lucky day, you can go. But the number of spores, all the Sclerotinia spores will be caught, and the number of spore changes will trigger the change of the impedance signal in the electric field. And through measuring the numbers of impedance signal change, we can directly measure the spore numbers. So we tested this hypothesis in our laboratory. So we had an in vitro detection set up in our lab. So we put spores to the sensor from high number to low number. We put as high as 220,000 spores, and then 20,000, and then 2,000, and 200 to 20, 10, and 5. So we saw that with the decrease of the spore numbers, we have a decrease of impedance signal, and there are good correlation between them. So we proved this biosensor can work on our spores, and even better, they can detect as low as 5 spores with this technology. And now we need to find the number that triggers the disease, and then we can set up our biosensor. So how could we do that? We set up a growth chamber study. First, we have to select a spore trap. We evaluated lots of spore traps from different companies because we need to use liquid samples. So we selected the last one was a trap from SKC for our experiment. We hope in the future we can have something different because this device is pretty expensive. So the experimental was conducted like this. We grew 46 canola plants in a growth chamber till flowering stage. A jar of sand containing germinating scoria was placed into the chamber, and a spore trap device was placed in the growth chamber, run continuously starting at the flowering stage. We were monitoring the plants for disease at the same time. We also took liquid samples and plated on culture medium every 24 hours, 0.1 ml per place with duplicate. And fungal colonies were counted 5 days after incubating at room temperature, and Sclerotinia colonies were identified. These are some samples of what we took from the spore collector, and you see this black scorcher body in the petri dish. The greenhouse setup looked like this, and we have a jar of Epichysia put in the growth chamber, and canola plants were growing there, and we also had a spore collector inside the chamber, and the disease symptom was monitored. And we want to find the spore number correlation with canola diseases. And we put the Epichysia in the growth chamber for 6 days, actually more than 6 days. So from day 1 to day 6, we have increased the number of spores sprout out from the Epichysia. With a low number of Sclerotinia, we had less severe disease symptom. With higher number of Sclerotinia, we had more severe disease symptom. And more importantly, we quantified the spore for the disease. Like we found that 10 Sclerotinia spores per mil collected in 24 hours in a 3.3 square meter growth chamber started to cause leaf infection. And right now, we are verifying the results in our greenhouse. And we also prepared our field for next year. We need to bring everything out next year to have a wholesale testing. So we have our experiment field for canola, and you can see we set up a solar panel to provide power for the biosensor and the spore collector. And we put our spore collector there as well. And we actually, you can see from here, so we put some of the scorcher body into the soil. That was all happened in early July. And in mid-August, we found disease symptom. And we opened one of the stem. You can see a scorcher body in there. Actually, I should have chosen a different background. So in late August, we found Epichysia in our field. So this field is ready for next year. We had 33% of disease symptom this year in the field. Now let me talk about our biosensor. So the biosensor was designed like this. We had an in-field inlet and filter on the top left. So that's the place our sample was injected into. And we had a diaphragm pump that is responsible to draw samples and fluid into the chip. We also have a buffer storage chamber and a waste disposal chamber. Like how this worked is like we had our sample loaded to the inlet, and our sample will pass through the surface, and Sclerotinia spores were trapped. And after washing away the non-specific bending spores and other things and dumped them to the waste, the spores were measured. So we will have a spore number measured on the sensor. And on the left hand, that's how big a sensor you can see in the lab. And then on the right hand is how we make the transmission of signal. I don't know if anybody in the audience know how it works. Good, me neither. We don't need to know that, I think, because you don't need to be an electronic engineer to use a cell phone. But we have our collaborators from the University of Alberta. They are engineers, and they helped us work towards the transmission of signals. So they told me they use Wi-Fi technology, and they use Bluetooth. And so these are the paragraphs they wrote. So they designed the user interface as a web application so that cross-platform devices, computers, can access the user interface. After reading this, I'm more confused. So in the summary, preliminary results showed a correlation between spore population in the air and disease incidence in a greenhouse growth chamber study. And a specific biosensor detector that can detect the spores at an acceptance level have been found. And the signal transmission from biosensor to an iPhone has been achieved. So right now, we can actually send the signal from the biosensor to a cell phone, but not yours yet. So in the future, we will try the same thing in the greenhouse, and most importantly, we have to do this in the field. So with the growth chamber results, the spore collector will be used to trap spores in the canola field and determine the number of spores that triggers the disease outbreak. So we need to further decide how big an area one biosensor can cover, so we can let you know how many you should put in your field. And the spore collector and the nano sensor now are separate pieces, so we need to put them together. And after all this work, we need to verify the results, at least 2 years in the field. And after all this work, I hope we can have a device in the field to monitor the Sclerotinia stem rot for you and alert you whenever there is a Sclerotinia stem rot outbreak imminent. And I thought you could set like alarm on your cell phone for this message. Like if they send you this message, you need to spray. I thought you could set up an alarm, like a fire alarm. But on the second thought, what if it happened in the middle of the night? You may fall off your bed, so that will be a safety issue. So you can do whatever you want, but I just want to make sure that you take this seriously. With that, I would like to acknowledge the funding supports from SDF, ACPC, AITF, and now Innotech Alberta, and our engineers from University, Dr. Chen and Dr. McKay, and plant pathology specialist, Jian Yang from Innotech Alberta, and our excellent technical support from Rodney Verizek from Innotech Alberta. And I also would like to thank you for your attention, and I wish you and your family a very Merry Christmas. Thank you.
So, do we have questions?
So, Xiujie, do you see this nanotechnology potentially being able to move over into, let's say, cereal world or cereal and germ or in wheat or something like that?
Right now, it's not because of the nano sensor, it's because we can only collect airborne spores right now. If the spores are airborne for cereals and other crops, it can be used there.
What's the cost on it?
Oh, yeah. That's a burning question. Can I not answer that? Actually, it's not that bad. The little chip I showed you there is 3.5 by 2.5 centimeters in diameter. And it costs $10 only. Like you have 8 little squares there, actually you can detect 8 different things. It costs $10. But you need a little thing to measure it. And right now, they give you that for free. Like you have a chip, you have to put it there by yourself. They give you that for free. But you use it for 1 year, then you have to buy another chip the next year. So $10 each year, I hope. That's all.
Okay, I guess that's it. So
Thank you.
another round of applause for Xiujie.